What is up, you guys? So in this one, we're going to talk about cone programming. That is, we're going to revise what an SOCP is and a QCQP is, and next we're going to see how to solve them using the CVXOPT toolbox. Okay? In case you don't know or you have no clue what SOCP is, I urge you to go back to my Convex optimization series, where I'm going to leave the link down in the description below on lectures concerning SOCP and QCQPs that are second order cone programming and quadratically constrained quadratic programs respectively. So without further ado, let's get started. So let's start by recalling what a second order cone program or an SOCP is. So we're trying to minimize a linear cost subject to some cone constraints. So we've got M cone constraints. The left hand side is a L2 or Frobenius norm, but we don't have a square here. And on the right hand side, we've got an affine term. We've also got an affine constraint here, fx equal to g. And so this is the SOCP program. Well, if you open CVXOPT documentation, you will find that it is a bit different. You're minimizing a linear cost, no problem. You've got affine constraint here, but it seems a bit different than what we have right here. So over here, we've got the cone constraints, right? However, right here, it's a bit different. And this is where we're going to, transform this problem into this problem right here so that we can solve the problem using CVXOPT. Now, what is the last constraint over here? It's telling you that the cone constraint is only on one vector S, where the cone constraint applies on all the entries except the first one, and the right hand side is the first entry. So it turns out that you can actually transform this constraint over here, the cone constraint, into gx plus s equal h, and s0 is greater than the norm on s1. So s0 is the first entry and s1 is the vector containing all the rest. For that, what we're going to do is that first we're going to introduce this s variable. So this s looks like this. S is s0 scalar and s1 vector, right? And so our job right now is to be able to rewrite this particular constraint as the gx plus s equal to h and s0 greater than norm of s1. Well, the first thing I'm going to do is just replace the indices by k instead of I, right? So I'll end up having this. So k instead of the I, right? And the second thing I want you to observe is that, notice here, since we've got the L2 norm appearing on the SK1, right, then it seems natural to take this term over here as my SK1. So what is SK1? Since here I've got K, so I've got KS vectors. So this guy is the SK, this is the S0K or SK0, and this is the S1K or SK1. Just for notation's sake, I'm going to be referring to S0K as SK0, same thing, and S1K as SK1. We're not going to confuse the indices here, so we can use them interchangeably. Right, so now, since this is the SK1, right, then we're left with SK0. So now, we're obliged to pick this guy as SK0. Okay, perfect. So now, if I want to come here and plug in the values in terms of A, B, C, D, and X, I'm going to end up with this. Right here, I've got my CK transpose X plus DK. And right here, I've got my AX or AKX plus BK, right? So the first term right here is a scalar and the second one is a vector. Okay, now let's express this as AX plus B. What do I mean by that? Well, actually, you can write this term as this. So this is CK transpose right here and an AK right here. we've got the x over here plus a vector that contains d and b. So dk and bk, right? dk is a scalar, bk is a vector. ck transpose is a row vector, ak is a matrix. So now we have the term actually that appears over here. We've got gkx plus sk. How? Well, this is a gkx. Well, it's not sk right now, but it's a vector, which is actually the h vector, right? So since this whole thing is the s, right? Actually, this is not the gk yet. This is minus gk. So if I denote this guy as minus gk, then we're there. Why? Since I've got sk is equal to this guy, right? Then right now I could write down, just get this guy on the other side. We've got gkx plus sk is hk, right? So what is my gk? It is minus this guy. So my gk is nothing other than minus ck transpose and ak. And my hk is dk and bk. As simple as that. And that's it. So now we wrote this SOCP problem in a different way. What is it? It is you're minimizing the same cost, nothing has changed, but this time subject to, instead of the cone constraint, we've got two constraints. What are they? It's the gx plus s equal to h. So gkx plus sk is hk for m such constraints, and sk1 in norm less than sk0. And to go from here to here, you need a change of, not variables, parameters. Since g is now expressed in terms of a and c, and h is now expressed in terms of b and d. So how do you go from here to here? You need those two equations. So to make things look better, I'm going to draw an arrow over here and say to go from here to here, you need two change of parameters. First off, the gk, which is minus ck transpose and ak, right? And the hk is your dk and bk, right? And now, once you do this change of bases or change of parameters, right, you can now solve your second order cone program using SOCP's CVXOPT. Let's do an example over here. Actually, this example is given right here, right? You've got, you're actually right here, the guys wrote the SOCP in this form right here, and they solved it, of course, using this form without explicitly saying, oh, we did this change of parameters, right? That we're going to do. So as an example of SOCP, we're going to solve this problem. So what is this problem? First, we have to minimize minus 2x1 plus x2 plus 5x3. What could this be written as? F transpose x, of course. Well, what is my f over here? If I write F transpose x, what is it? My f will contain the coefficients, minus 2, 1, and 5. So, minus 2, 1, and 5. Okay? No problem with the cost. Now, right here, you need to pay a bit of attention. Subject to those two cone constraints, right? We've got the first one and we've got the second one. Right here, my a, well, we can write both as akx plus bk in norm less than ck transpose x plus dk, right? the first set we will be referring to as A1x plus B1 in norm less than C1 transpose X plus D1, and the second one A2, B2, C2, and D2. Okay, so how do we do that? It's really simple. First, let me write the cone constraints down. A1x plus B1 in L2 norm less than C1 transpose X plus D1, and the same thing for the second one. And then we'll match the parameters A, B, C, and D for the first and the second cone constraints. Okay, so now what is my A1 and what is my B1? Let me write them all over here. A1 is actually a 2 by 3 matrix, right? 3 number of parameters, 2 number of rows or equations, right? Containing the coefficients, the linear coefficients. So minus 13, 3, 5, and minus 12, 12, and minus 6. So let's copy that down. Right, so minus 13, 3, 5, minus 12, 12, and minus 6. As over here. And my B1 vector is minus 3, minus 2. The constants that you see over here. So B1 is minus 3 and minus 2. Now what is my C1 vector and what is my D1 scalar? My C1 is like F. It's the vector containing the coefficients of x1, x2, and x3. So it's going to be minus 12, minus 6, and 5, right? And my D1 is just minus 12. So D1 is minus 12. Now using the same, approach, we can fill in A2, B2, C2, and D2. So my A1 is going to contain minus 3, 6, 2, right? 1, 9, 2, and minus 1, minus 19, and 3. There you go. Now my B2 is going to contain 0, 3, and minus 42. So 0, 3, and minus 42. My C2 is going to contain minus 3, 6, and minus 10. So minus 3, 6, and minus 10. And last but not least, the D2 will contain 27. So 27, right? Now we need another step to solve using SOCP by CVXOPT. What is it? As we discussed here, we need to go from this problem to this problem using the simple change of constraint. Now over here, since we've got two cone constraints, we're going to have two such batch of variables. So we're going to have G1H1 and G2H2. Well, here's my G and my H, right? So now let's fill up G1H1 first. So G1 is minus C1 transpose, then A1. So minus C1 transpose is going to be, first of all, what is C1 transpose? It is minus 12, minus 6, and 5. Then minus C1 transpose would be 12, 6, and minus 5. So 12, 6, and minus 5. Now let's stack beneath this vector the A1. Actually, it's minus A1 because we've got a minus here, okay? So minus A1 would be 13 minus 3 minus 5. So 13 minus 3 and minus 5. And 12 minus 12 and 6. So 12 minus 12 and 6. Right? Now my H1 is going to contain D1 along with B1. So D1 is minus 12 and my B1 is minus 3 and minus 2. Okay, now let's do the same thing for the second set of parameters. So G2, as we did with G1, will contain minus C2 transpose. So 3 minus 6 and 10. 3 minus 6 and 10. And right beneath it, we've got A2. So A2, actually it's minus A2. So 3 minus 6 minus 2. 3 minus 6 minus 2. Then minus 1, minus 9, minus 2. And 1, 19, and minus 3. Now we've got the H2 to fill up, and we're done. We're done formulating the problem, if you will. So H2 is D2, B2. Where's H2? Where's D2? It's over here. So that's the 27. And my B2 is 0, 3, minus 42. Okay, now we've got the four matrices, or the two matrices and two vectors that we want to solve our problem. Where are they? Well, they're here. There you go. Right? We're going to use them to solve the problem. Okay, now let's solve the problem on CVXOPT. So the first thing you'd want to do is, from CVXOPT, you'd want to import matrix and solvers, right? That's the first thing. The second thing you'd want to do is define your parameters within the problem that are the f, g, and h, g1, h1, g2, h2. But, within SOCP solver of CVXOPT takes G1 and G2 as one matrix G, where G1 is stacked on top of G2, and likewise, H1 is stacked on top of H2 for the H. So first thing I want to do is define my F vector, that is minus 2, 1, and 5. So minus 2, 1, and 5. You can go ahead and print it as such. Okay, the second thing you'd want to do is define your G. Well, let's start with G1 first. It's this matrix, so let's fill it up. So G is a matrix where its first column is 12, 13, and 12. So 12, 13, 12. Its second column is 6 minus 3 minus 12. So 6 minus 3 and minus 12. And the last column of G1 is minus 5, minus 5, and 6. So minus 5, and 6. As easy as that. Now, the second matrix, that is G2, is a matrix containing 1, 2, 3 columns. So 1, 2, 3 columns. The first column contains 3, 3, minus 1, 1. So 3, 3, minus 1, 1. The second column contains minus 6, minus 6, minus 9, and 19. So minus 6, minus 6, minus 9, and 19. And the last column contains 10, minus 2, minus 2, minus 3. 10, minus 2, and minus 3, right? So there you go. This is my G matrix. And now for my H, right beneath it, all I have to do is define H1 and H2, right? So my H1, I believe, is minus 12, minus 3, and minus 2. So minus 12, minus 3, minus 2. And my H2 is 27, 0, 3, minus 42. So 27, 0, 3, and minus 42, right? Now we're set. We've got my F, my G, and my H. Actually, let me get rid of this to make stuff look more beautiful. I'll do this. I'll remove this. Compile this. So I've got my F, G, and H. All I have to do is call solvers.SOCP, passing the F, the G, and the H. And we've got an error saying C must be a dense column. Okay, so to fix this error, all you have to do is just append a dot after each number. So 2 would be 2 dot, 1 would be 1 dot, and that's it. Then pass your F, G, and H as such, and you're ready to go. So after what, 9 iterations, the optimal solution is found. Well, how do we get it? Actually, how to see if you actually found the optimal solution? Well, you call in, you save the solver in, let's say SOL, solve, and then you call in sol status. It's optimal. Well, what is the optimal solution? It's sol of x. Well, it's 3 by 1, of course, containing x1, x2, x3, where these numbers are their corresponding values. So x1 is minus 5.01, x2 is minus 5.77, and x3 is minus 8.52, not 57. As such, okay? So really, this is how you know, if you're interested in solving an SOCP using CVXOPT, this is the proper way of doing it. You first write down the classical or standard SOCP, that is, minimizing a linear cost subject to cone constraints. Then you convert your cone constraints into, so each cone constraint translates to a simpler cone constraint in terms of S, and an affine constraint in terms of G, H, and S itself. Okay? What are the change of parameters? Well, they're G in terms of C and A, and H in terms of D and B, as we did over here in this three-dimensional example. Okay, another interesting problem is quadratically constrained quadratic programs. And this is based off a comment by Louis Wang Shang, where he says, "Hi Ahmad, thanks for the great tutorial. Could you talk about how to use CVXOPT to solve convex QCQP problems?" Well, this is very interesting, I think, and the reason why is because once you open the documentation of CVXOPT and once you go to quadratic programming or even cone programming, you don't stumble upon QCQPs. And the reason why is because a QCQP could be written as an SOCP, right? And actually you can also write a QCQP as an SDP, a semi-definite program. But we're going to stick with what we explained right here, an SOCP, and try to write down a QCQP as an SOCP so that we can make use of the SOCP solver of CVXOPT, okay? So what we're going to do here is simply convert a QCQP into an SOCP. This could always be done, but you cannot go the other way around. That is, you cannot always go from an SOCP to a QCQP. So SOCP is more general, right? So how do we do that? How do we go from a QCQP to an SOCP? The first thing you'd want to notice is that we're going to use the epigraph form. That is, instead of minimizing this function right here, this quadratic function, we're going to minimize something simpler, which is linear in terms of our variables. That is, we're going to write this as we're minimizing a scalar gamma, where gamma upper bounds the initial cost, that is x transpose px plus x transpose q plus r. It's always upper bounded by gamma, right? By doing so, we have added one variable to the problem, that is gamma, right? So that's the first step. The second one is to actually decompose my p's, that are pi and p, as A transpose A. And the reason we do that is because the SOCP has cone constraints. So you've got an L2 norm on AX plus B. And why do we care about A transpose A? It's because due to the expansion of the norms. So once you take AX plus B in L2 norm squared, this is actually X transpose A transpose AX plus 2 X transpose A transpose B, or this could be written as B transpose AX, right? Plus one more term that is B transpose B, okay? And so you see that the quadratic terms have A transpose A. So we need our A to show in the constraints, right? So why not pick A transpose A to be my P? So by doing this change of variable or change of bases, we're going to express my P as A transpose A, right? And likewise my PI as AI transpose AI, okay? By doing so, we arrive at the following problem. So we just replaced each PI with AI transpose AI and the P with A transpose A. Now, in order not to confuse notations, I have my A here and I have another A which has nothing to do with this A. So I'm going to go back here and erase what I had here. Instead of AX equal to B, I'm going to write down FX equal to G. Okay, I'm going to replace this over here and this over here so as not to confuse notation. Right, so now instead of my AX equal to B, I have an FX equal to G. Okay, so now after this change of bases, what we're going to do next, notice that what we're doing here is we're trying to approach the L2 norm as much as possible. So I'm trying as hard as I can to get X transpose A transpose AX and 2X transpose A transpose B and B transpose B. Well, the next thing to do is that since I've got affine terms showing here, so X transpose QI and X transpose Q, so instead of my, Q, I'm going to insert 2A transpose B so that I have this term now showing up. Now I have this and I need this, right? How to do that? Well, instead of the Q, I put in 2A transpose B. So my Q is 2A transpose B and my QI is 2AI transpose BI. And what I get is the following. Okay, now I've got the blue terms right here reflecting this change of variable, the A transpose B instead of the Q, right? So now I've got the first and second terms of the norm, right? I've got this and I've got this. All I need is this constant right here, that is B transpose B. Well, that's easy. All you need to do is add and subtract that term in the quadratic constraints. So let's do this. Call this step add/subtract B transpose B in the second quadratic constraint, and in the first one we're going to add and subtract BI transpose BI, right? What we'll get is the following. Okay, so now I've got my terms. What are they? I've got X transpose A transpose AX appearing up and down. I've got 2X transpose A transpose B appearing up and down. And I've got my B transpose B appearing up and down. In the first quadratic constraint, here they are. And those could be replaced by the norm square, right? In the second one, they're over here. So those, we could replace them by the norm as such. So now we've got the norms right here, right? And we've got some constant terms over here, except for the gamma, of course. So what we're going to do now in the next step is just bring what's left onto the right hand side, okay? We're going to throw them here. What we're going to get is the following. And there you go, okay? We're really close now to the SOCP form. That is over here. We've got our fx equal to g, we've got our f transpose x, and we've almost got the cone constraint, except that we've got a square over here. Well, how do we go over this. How do we bypass this problem? Do we take a square root as such? Well, the square root might work for the first one. That is, if I take the square root on both sides, I'd end up with something like this. So I'll get an AI x plus bi in L2 norm less than the square root of this guy, which is a constant. So my C transpose X over here, I don't have a C. I don't have an X over here, and I don't have a gamma. So my CI's are 0. As a note over here, my CI's are 0. CI vectors, of course. So I'm left with a DI, where my DI is nothing other than the square root of BI transpose BI minus RI, right? Simple as that. So taking the square root on the M cone constraints works, okay? It works. However, it doesn't work directly on the second one. Why? It's because you've got a variable over here. It's peaking over there. You can't just insert a square root right here and just expect to have, a cone problem. Why? It's because the SOCP does not tell you, oh, I have a square root on one of my variables. Okay? That's not the right way of doing it. There is a trick over here that a lot of people do. And the trick here is to add one more inequality but affine constraint telling you that your gamma is less than a certain number, t. Once you say that, you can go ahead and here and say simply that this guy is less than t plus b transpose b minus r, okay? And now this guy is a constant and t is a predefined parameter. So it's a, if you will, it's an upper bound on one of your variables, gamma, okay? So now what you can do is, okay, since this guy is a constant, I'm going to do the same thing as here. Say that my C, I don't have a C transpose X and I don't have a C gamma over here. So my C is 0 and my D is the square root of T plus B transpose B minus R. Okay? Now you've got an SOCP. As simple as that. How does it look like? Well, there you go. So you've got your cone constraints right here. Okay? You've got M plus 1 cone constraint. You've got affine and 1 inequality constraint. Okay? You could set t to be really high to ensure that your variable does not trespass this t. And that's it. So you can actually use what we did. So using the SOCP, solve your QCQP as such. Things to keep in mind are the following. Well, over here, you need a square root decomposition of a matrix. This is ensured using the Skippy library. And so from Skippy, what you'd want to do is go ahead over the linear algebra subpackage and import the square root for matrices. Okay? So in that case, if you've got, I don't know, let's say you've got a P that is 5, 3, and 3, 4. Okay? Let's print the P to see, not O, P. Okay, so this is your P. Well, how do you go from P to A? It's easy. All you have to do is call A is square root M of P. How does your A look like? Let's print it. There you go. And to ensure that A transpose A is actually P, all you have to do is np.matmul, matrix multiplication of A transpose with A. NP is not defined, sorry about that. Let's import it right here. import numpy as np. And there you go. So A transpose A is indeed P. That is 5334. Okay? So that's one thing to keep in mind because you need your A. That's one way of extracting A from P. The second thing you'd want is your Q. Okay? Your Q. How do you get your Q? Well, you see that Q is 2A transpose B. Okay? And B is not given in the initial problem and A is not given. Well, we got A over here. How do you get B? From Q and A. So your Q, let's say your Q was given to be something like 1, 3, okay? How do you get your B? So your B is actually, using this, it is half A transpose inverse times Q, right? Because from here, you can, using some simple linear algebra, you could write this as B is equal to half A transpose inverse, right? Times Q. That's if A is square. If A is square, then A transpose is square. Then you can invert. And if not, you'd have to go to a pseudo inverse, okay? But P is square. It's always square. No matter what your problem is, it's always square. No rectangular matrices involved in P due to the construction of QCQP, okay? So A is always square and hence this is always applied. So from, you do a 0.5 times, you need to multiply the inverse of A transpose, so MP lean algebra dot inverse of A transpose. You're multiplying this guy by the Q, okay? There you go. And that's it, okay? So those are stuff to keep in mind when you want to go from a QCQP to an SOCP. From P, I want my A, and from Q, I want my B. Well, you should always get your A before going to get your Q. Okay, so what other stuff do we need? We've got the A and we've got the B. Let's see what we've got here. The gamma is part of the well, your F over here, if you were to write the cost as F transpose X as the initial problem, so your F over here would be, this is actually F transpose, I'm not going to say X, I'm going to say Y. What is Y? Y is actually gamma and X. So my F would turn out to be a vector containing 1 and all zeros. So that F transpose Y returns gamma, okay? And a very similar rearrangement could be done here so that you've got only your problem in terms of Y, so that you can go back to the initial SOCP and solve it using CVXOPT, okay? So that's about it. That's all I have to say in this lecture. We pretty much did a lot of stuff. We talked about what an SOCP is, even though I have a really detailed lecture on second order cone programming in my convex optimization series that I'll leave down in the description below. We revised what SOCP is and wrote it in a different way so that we could match the problem with that of CVXOPT in terms of S0 and S1. We showed how to do that. Instead of my C and A, I'll get a G, and instead of a D and B, I'll get an H, so that our problems match. And we showed how to solve an SOCP example. So this particular example that is also given in this documentation, we showed how to solve this using CVXOPT. Next, and based upon Louis Wang Sheng's request, we also talked about quadratically constrained quadratic programs. we revised how they look like, and we showed in details how to go from a QCQP to an SOCP. That is over here. So this guy is an SOCP. And we also showed how to write down the parameters of the SOCP in terms of the QCQP. So my A is the matrix square root of P, and my B could be computed from A inverse and Q, so that you could, solve your QCQP using the SOCP formulation. Now, just a very small note over here. This is standard SOCP. You'd want to do one more arrangement before solving using CVXOPT. That is, as we did in the SOCP in the first part of the lecture, you're going to have to go from A, B, C, D domain to G, S, and H domain. So there's one more change of parameters that has to be done, okay? Which we already did in the first part of the course, right? So one step ahead you could take to solve the QCQP using CVXOPT. Thank you so much for watching. If you found this video beneficial, please leave a like on the video, subscribe to my channel. If you have any questions whatsoever, kindly leave a comment down in the comment section below, and I'll make sure I'll get to it as soon as possible. Also, if you could donate to my Patreon account. You can donate an amount of $3, $20, or $40. Those are the options I give. So, thank you so much for watching this lecture, and I'll see you then.